great. Let's continue with the trig substitutions. That's what we were talking about last time. Trig substitutions. Before this, we talked about trigonometric integrals. That is if you're actually doing the integral of some kind of weird thing involving sines and cosines. Those are called trigonometric integrals. And you handle them differently if the powers are even or odd. The trig substitutions is for certain types of integrals that don't seem to have anything to do with trigonometry, but you make a substitution to turn it into sines and cosines. And there are actually two types of these substitutions that we're going to do. The one that we discussed last time, and I want to do some more examples of that this time, is this one. If you see square root a squared minus x squared, where a is some constant, do the substitution x equals a sine theta, and dx would be the derivative of that, which would be a cosine theta d theta. And then use 1 minus sine squared theta equals cosine squared theta. This is the first type of the trig substitutions that we're going to talk about. If you see square root a squared minus x squared, then this is the appropriate substitution that you should do. The other one, just a little spoiler alert, is what if it's a plus rather than a minus? Then there's a slightly different thing, but we'll get to that later on. But this is the first type of the trig substitution. We did one example last time. I'm going to do one now, and then I got one for you all to try. It's a fairly, like if you can remember what the appropriate substitution is, it's a fairly simple trick, but then you have to do lots of simplifying, and there are many opportunities to mess it up, which is what makes it a little tricky. Anyway, let's just try this here. All right. Let's try this here. So this does fall into this category that you see up there. If you see square root of a squared minus x squared, I do see that, where in this case the a would be 3, because I see 9 minus x squared there. All right. And so we are going to do the substitution as described up there. Maybe I'll just say, actually, this one, I don't know if you noticed, but you can actually do this one with an ordinary u substitution. If you call the inside here u, then the du would be negative 2x, and the x out here will allow that to work. But I want to do this with the trig substitution just to demonstrate the method. There are many other examples where you can't do it by any simpler way. So this one, I am going to do what it says up there, x equals 3 sine theta. I picked 3 because what I see inside the squared is 9, which is 3 squared. And then dx is the derivative of that, which is 3 cosine theta d theta. All right. And we're going to plug those in and simplify a bunch of stuff. We are also going to change the boundary values in the integral sign, and this is sometimes a pain to do, but we can handle it. So we need to consider when x is 0, what is the appropriate value of theta? If x is 0, then when I write x equals 3 sine theta, of course this means 0 equals 3 sine theta. You could divide the 3 across and it'll say sine theta equals 0, which means theta equals 0 because the sine of 0 equals 0, right? And this you have to think through. When I say sine theta equals 0, what is the angle where the sine of that angle is 0? The answer is it's 0. So the theta value corresponding with x equals 0 is also 0. So that means when I rewrite this in the substitution, I still put 0 down there, right? The original 0 referred to this value of x equals 0, but after doing the substitution, it's now theta equals 0. They are the same. The other value is not going to be the same. So what about the other value? That was x equals 3/2. Here I have to translate this into a theta value. I'm going to do it the same way. I say 3/2 equals 3 sine theta, and I want to solve for theta somehow. Divide by 3 here, right? I'm trying to solve for theta. Dividing by 3, it says 1/2 equals sine theta. And now you need to know what is the angle whose sine is 1/2. I'm thinking of a angle that fits a triangle like that, right? Here the sine would be 1/2. Anybody know what's the angle there?
Pi over 6.
Pi over 6, yeah, 30 degrees, also known as pi over 6. Great. So I hope you all remember your little triangles like that. You have to sometimes figure this out. So that's the upper value in this integral. Pi over 6, right? You got to do a little business to translate the boundary values. All right, anyway, now we can proceed with the substituting. So every x becomes 3 sine x. So the x out front, I got 3 sine x. Theta, not x. 3 sine theta, and then I have square root 9 minus, and then x squared becomes 3 sine theta squared. And we should square both of those, which makes it a 9 sine squared theta. And then I have, that was the square root part. And then I have dx, which is another bunch of stuff, right? Dx is 3 cosine theta d theta. So outside of the square root sign now, we have 3 cosine theta d theta. All right. A lot of little bits there. And now we should try to simplify all of this as much as possible with the intention of eventually doing the integral. So I have a 3 on the inside of the integral, which can be taken out. And actually there's another 3, right? There's this 3 here and this 3 over here. Both of them can be pulled all the way outside the integral. So that's a 9 outside. And then I got sine theta in front. Here, inside the square root, we can also factor out that 9, but it comes out as a 3 because I'm going to pull the 9 out of the square root sign. So this is like 3. And then that's what remains inside the square root. I factored the 9 out, but because it's inside of a square root sign, it comes out as a 3. And then we got cosine theta d theta at the end. All right. I still have this weird square root sign, but here's the sort of second part of the trick, and really this is the entire purpose of the whole substitution. Remember I said up here, you do this and then you do this. So I see 1 minus sine squared inside of the square root sign. I make that a cosine squared, and the whole point of this whole thing is that this turns into a cosine squared, and then you can take the square root of it.
How do you get the 1 minus?
That comes from factoring 9 out of both of these parts. So this 9 becomes a 1, and then this becomes that when you take the 9 out. Yeah.
Is the 3 on the outside of the square root from the 3 cosine theta?
It's from this 9. So maybe I should have put an extra, if you like, just to clarify. I kind of did 2 things at once there. This 9 out here came from that 3 and also that 3 becomes the 9. They're all multiplied in there, so they factor out. And then the rest of it, I go sine theta, and then in here, factor 9 out, like this. Sorry, this 3 has been cared for already. And then, when I have square root of something times something, it makes the square root of the 9 times the square root of this. And that's where this 3 came from, the square root of the 9. Yeah. A lot of ins and outs there, all right? But anyway, that 3 now can pull out of the integral sign, and then this 1 minus sine squared is the same as cosine squared. So in front now I have 27, 0 to pi over 6, and then I got sine squared. This becomes square root cosine squared, and then I have cosine theta d theta. And square root of cosine squared is just cosine. And that step is actually the entire reason why we did any of this business, was it allows you to get rid of the square root sign. Sorry. You do the square root and it turns into just cosine, not cosine squared. All right. The square root sign is now gone, which I like. And then I suppose you could put those 2 cosines together. These are all multiplied. So what we have here is, I'll write it down here, 27 integral sine theta times cosine theta squared, or cosine squared theta if you like. All right. And that's as simple as this is going to get before we do the integral. Unfortunately, there's still a multiplication in there. Anybody have an idea how can we do this integral? Yeah? You could, but that's not a good idea. That actually would make it kind of worse if you did that, I think. Anyone have another idea? It's not wrong. It's just it unfortunately is not going to make it happen. Yeah. Parts is another idea that in theory you could do, which in this example isn't going to work. I like these ideas, although they are bad. They're not necessarily bad, but yes, bad. Any other ideas? This actually is a trigonometric integral. It is just powers of sine and cosine, and one of them is an odd power. That's like sine to the 1, cosine to the 2, right? And in that case, the trick that we use is save one of them and then do a u substitution. And actually, the way it's written, we already have sort of one which is saved, this sign, and the appropriate u substitution. So this now, I will just say, this is a trig integral with an odd power. Odd meaning sine to the 1, and 1 is odd. And so the appropriate thing to do here is a u substitution. U equals cosine theta. Du is negative sine theta d theta. So this is of the type that we talked about, I guess, 2 times ago. So I'm not, it's not a scandal if you don't remember this, although you should remember it by the time we do our quiz on this topic. All right. We do the u substitution. So let's see if we can make that happen. 27 is out here. And then, so cosine theta becomes u. And so this right here is u squared, right? And then what's left over? Sine theta times d theta. And that is negative du, right? If I move the negative sign over. So these guys together gives me times negative du. That's this part. Sine theta and d theta is negative du. All right, so this becomes, pull the negative sign out, negative 27 integral u squared du. Do the integral, negative 27, it is 1/3 u cubed. All right. Now, do you put the plus c or do we have some values to plug in? We have some values to plug in, 0 and pi over 6. So those are theta values, so I should replace the theta variable first. So this u I'm going to replace by cosine theta, and then plug in the values. 27 times 1/3 is 9, right? So this is negative 9 cosine theta cubed. I'm plugging back in for the u. And now we can plug our 2 values. Our theta values were 0 and pi over 6. So I got minus 9 and then cosine pi over 6 cubed minus 9 cosine 0 cubed. This is the answer basically, although let's just simplify all the way if we can. Cosine of pi over 6, remember pi over 6 is this triangle, which has a root 3 on that side. This is the 30 degrees over here, pi over 6. And the cosine of that would be root 3 over 2. It's the adjacent over the hypotenuse. So this will be my real final answer. Negative 9 root 3 over 2 cubed minus negative 9, that's plus 9. And then cosine of 0 is 1. So 9 times 1, which is just 9. All right, that's quite a journey, I would say, but that's how we do it. Anybody got questions or feelings about this? This is how we do the trig substitution. It's basically like the idea of it is just this in the box, which is not so hard to understand and remember. But I think really what makes these hard to see it through, at least, is to do all of the appropriate simplifying steps. And then you have to know how to do this part, which, can be a little tricky. All right. Like I said, I had one for you all, but I want to, let's do one for you all. All right. How about you try integral from 0 to 2 over root 2. That's weird. X squared over square root 4 minus x squared dx. See what you think. You should use all the same tricks. Well, a lot of the same tricks at least. Talk to your friends about it if you like. It's also 1, because 1 squared plus 1 squared is 2. Does that make it which side is
Yep.
Can we talk about these? I see most people are still working on it, but just so that I wanted to do a few more today. These, in my opinion, are quite difficult. I mean, even if you know exactly what you're doing, it'll still take you quite a while to work through all the details. And if you're like me, you're liable to mess it up at some point along the way. But I mean, everybody got it started off well, at least. The appropriate substitution that you're going to do is this. X equals 2 sine theta, and then dx is 2 cosine theta, d theta. And I'm going to start by translating the boundary values. And for this, you need to have a fairly good recall of your basic trigonometry facts. So the boundary value of x equals 0, I say 0 equals 2 sine theta, and then try to solve this for theta. I can divide the 2 and it goes away. It says 0 equals sine theta, which means theta equals 0 because sine of 0 is 0, and that's the angle whose sine is 0. All right. And then the other boundary value would be x equals 2 over root 2, and so that means 2 over root 2 equals 2 sine theta. We can cancel these 2's on either side. Dividing both sides by 2 gives me 1 over root 2 equals sine theta. And I think of this, I mean, you can, if you like, maybe you just have all your values around the unit circle memorized and you just know which angle has sine equal to 1 over root 2. I don't really have those memorized in that way. I think of a triangle where the opposite side is 1 and the hypotenuse is root 2. And this I recognize as being the 45-degree triangle. The two triangles that everybody knows are the 30, 60, 90. That one has the sides of 1, 2, and root 3. And then there's the 45, 45, 90, which has sides of 1 and root 2. So this is the 45-degree triangle, otherwise known as pi over 4. So that's the appropriate boundary value there. So these you may want to review yourself a little bit. These are important to know how to do that as a step. Okay, so I am ready to proceed with the substitution. The lower value of 0 is still 0 because x equals 0 is still theta equals 0. The upper value, 2 root 2, becomes pi over 4. And then I'm going to plug everything in for the substitution. Up top, I have x squared. That's going to be 2 sine theta squared because x is 2 sine theta. And then on the bottom, square root 4 minus 2 sine theta squared. And then dx, the dx is important because it becomes this other stuff, 2 cosine theta d theta. I hope I'm doing all right so far. Any questions so far? And now is the time when things kind of go haywire if you're not good at simplifying stuff, but you got to simplify this stuff. So up top, 2 times sine theta, the whole thing squared. You square each of those guys, and I get 4 sine squared theta. On the bottom here, I have 4 minus, again, square that thing, 4 sine squared theta. And over here, I guess this will just stay like it is for now, 2 cosine theta d theta. Any suggestions? What did you do next? Yeah?
Pull out the 2.
Pull out the 2? Sure. And the 4, how about that? We can factor these extra constants out of the integral entirely. So that'll be, is that what you meant?
Yeah, pull out.
Yeah. You can also pull out the 4 from the square root down here, right? And when you factor it out of the square root, it becomes a 2. So what she said, take out this 4 and this 2, that's an 8 on the outside. And then I have sine squared theta up top. You can also factor 4 out of the square root and it turns into a 2 when you pull it out, like so. And then out here we still have cosine theta d theta, all right? And now that 2, which is in the denominator, can factor out of the integral. It'll factor out as a 1/2, and so we have a 4 on the outside. What else did you do next? I know some people got this far. What should I do next? Yeah?
Rewrite 1 minus sine squared as cosine squared.
Yeah, great. As square root of cosine squared. So this is sine squared theta up top, and then square root cosine squared. And then the square root of cosine squared is, of course, just cosine. So 4 integral 0 to pi over 4 sine squared theta over cosine theta d theta. And if you haven't screwed it up already, everything works perfectly so that those cosines will cancel, right? And I feel like a good boy. It turns into just integral of sine squared theta. So this is 4 integral 0 to the power of 4 sine squared theta d theta. All right. We're not done, of course, but I'm feeling pretty good about this at this point. Any question how we got here? Where do we go from here? Anybody remember the appropriate thing to do with integral of sine squared theta? Yeah?
Plug in 1 minus cosine theta.
Yes, something like that. So this is one of the rules that we used last time. Sine squared theta equals 1/2 1 minus cosine 2 theta. I think this is something like what she said. All right, this was from those double angle formulas or half angle formulas, however you like to say it, that we were using last time. This is a trigonometric integral of the type where the powers are all even, and so we have to use these rules for it. So that is going to become 4 on the outside, integral sine squared theta is 1/2 1 minus cosine 2 theta. So you got to remember how to do those other tricks too. All right, factor the 1/2 out of the integral. It joins with the 4 and becomes a 2 integral 0 to pi over 4, and then I just have 1 minus cosine 2 theta. And this we can just straight up do the integral. So we get 2 on the outside, and then 1 becomes theta. Negative cosine 2 theta becomes negative 1/2 sine 2 theta. And then not a plus c, plug in the values like that. I hope you all remember. I'm using the integral of cosine k theta is 1/k cosine k theta. We did that last time. All right, and now plug the values in, and we'll try and simplify this all the way just for fun. So I get theta is pi over 4 minus 1/2 sine of 2 times pi over 4. That was the first value, pi over 4, and then minus, plug in the second value of 0. So it's 2 theta minus 1/2 sine of 2 times 0. All right, and just to simplify everything, pi over 4 is what it is, and then this part 1/2 sine of, I guess, pi over 2, because that's 2 times pi over 4 inside there, minus 2, sorry, I wrote theta here. This should be a 0. I'm plugging in theta equals 0. I wrote theta. Theta is like a 0. There. Everything in the second parentheses is 0, right? It's 0, and then I have sine of 0. So this is all 0. And so my final answer, 2 times pi over 4 minus, what is sine of pi over 2? It is 1, yeah. Pi over 2 is 90 degrees, sine of that is 1. So this is just that. And that's it. Distribute the 2 if you want. Pi over 2 minus 1 is the answer. All right, quite a journey in my opinion, but that's how we do it. Anybody got questions about that? These ones, like I said, they will take you quite a while to do, even if you do every step perfectly right. If you don't do every step perfectly right, you're usually completely screwed. Like you just won't be able to finish at all because it has to work out perfectly. All right. Great. We got some time. I wanted to talk about a variation on this one. these things can actually be, I know as I was walking around, a lot of people were kind of stumped by just these values at the very beginning here, right? And you have to remember some of your old school trigonometry to convert the values. Unfortunately, it's actually sometimes a little bit harder if you don't have the values. Like typically, when you're doing the integral without values, I mean the indefinite integral, all you do is just put the plus c at the end and that's all there is to it. But actually on these, there's kind of a little extra bit of tricky business. So I will say for indefinite integrals, that is to say no two values, right? The ones where you just put the plus c at the end. These are actually even a little trickier. There's a different little thing that you have to do that comes right at the end. So I will say a bit tricky. For example, let's just try to do exactly the same example, but without the two values, right? You might say, isn't it just going to be the same? You put the plus c at the end and that's it? My answer is not quite the same. It's mostly the same. But how would we do this? Okay, we're going to do the same substitution as before. So I begin in exactly the same way. X equals 2 sine theta. Dx is 2 cosine theta d theta, right? And can I just say, do the same stuff, the same substitution. Everything is all the same until the very end when you would go to plug in the values. It's just we don't have the value. So can I just say, it's et cetera, et cetera, et cetera, dot, dot, dot. Can we just pick it up at the end? All the same algebra, like simplifying is the same until right here, I suppose, right? This is the point at which we have the two values to plug in. So we are going to get this exact same thing eventually. Duplicate and drag it down like so, right? But instead of the values, I put the plus c, and that's all there is to it, right? Now, what's tricky about this is when we write the answer of, the whole point is finding the antiderivative of this function. I should write the answer in terms of the original variable x. And with a normal u substitution, that's always easy. You just write down what is the u in terms of x. But actually, you will notice it's not at all convenient to do that in this example because we have, what is theta? You can't just go up here and say, oh yeah, theta equals whatever, because that's not the way that we did this substitution. So this is the tricky part. Now replace the original variable. Of x. In a traditional u substitution, this is always very easy to do because you always had a formula like u equals something in terms of x. But we don't have a formula theta equals something. We only have these formulas, x equals 2 sine theta. So the way that we have to do this is, starting from here, we have to solve for theta. Because my goal is to replace this theta by something else in terms of x. And so we need to solve for theta here. And how do we do that? Well, you want to isolate theta on one side. So I would divide by 2 first. It'll say sine theta equals x over 2. All right. And then how do we solve for theta here? Anybody know what's the appropriate thing to do here to solve for theta? Don't say divide by sine. Sine is not a thing that you divide by because it's not multiplied in there. Yeah. It is the inverse sine or the arc sine. So this is inverse sine of x over 2. That's how we solve for theta in a formula like that. All right. And so that's how we replace this variable at the very end here. So this whole thing here, and this will be my final answer. 2 theta is inverse sine x over 2 minus 1/2 sine of 2 times theta, which is inverse sine x over 2. And that's my answer. Strange but true. This is a weird final answer. But you have to write your final answer using the variable from the original problem. All right. Can we try one other example just of doing this last step here? So, because I mean the rest of the whole problem is a long and drawn out bunch of algebra. But just to practice this very last step here, let's try the other one, the one that I started off with today, x square root 9 minus x squared. All right. This was the one that I did at the very beginning. And again, I'm going to skip all the steps in the middle because they are exactly the same as the steps in the middle that we did at the beginning today. But I will just say same substitution and steps. I should write what was the substitution. It was x equals 3 sine theta dx equals 3 cosine theta d theta. All right, and we do the same substitution, and eventually it ended up with, I'm going to look at my paper here. You should have this on your paper too. It looked like minus 9 cosine theta cubed, and then we plugged in values, but I'm doing it without these values, right? And so it'll be just minus 9 cosine theta cubed, and I'm going to put the plus c at this point. So doing the exact same trigonometric substitution from that example leads us to this. And now we must replace the theta in terms of x. And so again, we have to solve for theta now in terms of x. So right here, x equals 3 sine theta. Solve for theta in terms of x. So I would divide by 3 first. Sine theta equals x over 3, and then theta is inverse sine x over 3. And that's what we're going to plug in for the theta. So my answer here shall be minus 9 is like so, and then cosine of inverse sine x over 3. That whole thing cubed. Right? And just for fun, just to make it one more little bit of interesting, I might say in a problem like this, simplify all inverse trigs. This is something that we have actually talked about before. How can you simplify cosine of inverse sine of something? That actually is something that we've done in the past. You draw a little triangle representing this inverse sine, and then you take the cosine of that triangle. I hope you remember. I think you'll remember as soon as I write this. Inverse sine x over 3. So I'm going to draw a triangle for inverse sine of x over 3. That is, it should be a triangle where here's my angle, inverse sine x over 3. The opposite over the hypotenuse apparently is x over 3. Because this is supposed to be an angle where the sine of this angle equals x over 3, and the sine is the op over the hype. So I put x is my ops, 3 is the hypotenuse, and then I want to find the cosine of that, because that's what I'm looking for up here, is cosine of this whole business. In order to find the cosine, we need to find the other side length. Maybe I'll call this just temporarily a here, and it'll say a squared plus x squared equals 3 squared, which is 9. So this says a squared equals 9 minus x squared. I'm trying to solve for x, for a, I mean. So this side of the triangle is root 9 minus x squared. That means the cosine of that angle is So the cosine of this is adjacent over hypotenuse, which is root 9 minus x squared over 3. And this is what I'm going to put in right here. Cosine of inverse sine x over 3 is that. Root 9 minus x squared over 3. So that means my final answer, sorry, I gotta scroll this a little bit. So my final answer is -9, and then all of that stuff, cosine of inverse sine, that simplifies to square root 9 minus x squared over 3. And it's that cubed, because it was cubed before. This is what we get. A little extra business at the end with the inverse trig functions. I hope you remember, we have done stuff like this a couple weeks ago maybe. All right. Excellent. What do we got? We got 10 minutes. I think I had one more I wanted to do, but this one more is probably going to take 20 minutes just because of how long these things go. Maybe I'll just say, I'll tell you the other kind of trig function, or the other trig substitution. Another trick, all right? The one that we just did is if you see the square root of a squared minus x squared, you do this and that. This one is if we see square root a squared plus x squared. The only difference is plus rather than minus. It changes the substitution that you have to do though. If you see this, then you do x equals a tan theta. It turns out using the tan makes this substitution work. These are a little, I mean, the algebra is a little messier maybe, because the dx would be the derivative of this. Anyone happen to remember the derivative of tan? It is secant squared, yeah. So the derivative is that. A secant squared theta d theta. And the reason you do the trig substitution of the other type was you turn something into a 1 minus sine squared and then you make that into a cosine squared. In this case, you do this substitution and then use, there is a similar rule for tangents, but it uses plus, and this is why this substitution works. 1 plus tan squared theta equals secant squared theta. So the details are all slightly different, but it's the same basic setup and the same basic kind of substitution tricks that you're going to use. All right, and maybe we will do this next time. Sorry to let you go so early. A little announcement next week. Next week, I believe, is the last week before spring break. Is that right? We will. I am planning to have a quiz on Friday, so be there. If you know you're not going to be there, then I will grumble at you. Let me know ahead of time, and you can do the quiz ahead of time. If you just don't show up, then forget about you. All right.